Okay, we will solve problem number 3.6.3. This is design problem. This is design problem on singly reinforced beams. I will read out the problem. Calculate the area of steel required for a singly reinforced concrete beam 230 mm wide and 400 mm deep to resist an ultimate momentum of 60 kN period. Assume concrete mix M20 and Fe 500 grade of steel and effective cover equal to 40 mm period. So this is the problem. We have to find out the ultimate moment of 60 kilometer will be resisted by this beam, and we have to find out for this moment how much area of steel is required. So again, list out the given things. FCK as usual 20 Newton per millimeter square. Fy here grade is 500, so we have to take this as 500 Newton per millimeter square. B is given 230, that is most common width. D, capital D is given 400 millimeter, and small d is given effective cover 40 mm. So easily we can say or we can find out small d, that is capital D minus d dash, that is 40. So it will come to 360, right, mm, and this beam has to reduce this ultimate moment or maximum moment, that is 60 kilonewton meter, and our job is to find area of steel required for this singly reinforced beams. So on the background, let's try to solve this program. First thing is we have to decide whether it's under reinforced or balance or over, right? So there are many ways we can find out whether it is under reinforced. So we can find Ku max, right, and then multiply it by D to get the XU max, right? So we need the XU max and then we need the XU to compare both to decide whether it's under higher or over reinforced or the balance design. But another way we can do, because we have the D, we have the value of the D, okay, that is given, that is 360 mm. Then we have given as moment resisted by this is equal to 60 kilonewton meter. So this is the moment resisted by the given beam. So if we find mu max or the ultimate moment resisted by this load and we compare both of them, then also we can decide whether this is under reinforced or the over reinforced. So let's try to find out the XU max and the MU max. Basically we need the MU max, right, to compare with the XU or given moment or the moment that is actually acting on the beam, and this is mu max, the maximum moment that beam can handle. So the formula for this, we know that FCK 0.36 FCK into XU max, right, and into bracket D minus 0.42 XU max, right. So we don't know this XU max. Let's try to find out the XU max. XU max is equal to, we know the formula, that's 700 into D divided by 1100 plus 0.87 into Fy. So this is the same formula we did earlier. We used this earlier. 700 into D is 360, small d again, remember that, 1100 plus 0.87 and Fy here is 500. So if you plug in the values, we get XU max equal to 164.17 millimeter. Now use this to find out the mu r max or mu max, ultimate moment maximum. So formula again I will write it, 0.36 fck, 36 fck into b into x u max, right, into bracket 1 minus 0.42 x u max. So we now have these values are all the values, just plug in all values. 0.36 into fck is 20, b is 230, into xu max we just calculated 164.17, into the bracket value 1 minus 0.42 into 164.17. so simplify this or calculate this, so you will get 79.13 into 10 raised to 6 Newton millimeter. So let's convert this into kilonewton meter. So divided by this value, that is 10 raised to 6. So this MUR max in kilonewton meter will be equal to 79.13 kilonewton meter. So our given moment or acting on the beam is mu, that is equal to 60 kilonewton per meter. This value is less than this value. That means this is for the balance, right? This is for the balance. Maximum value is for the balance. So if it is balanced, this value could have been this. So mu, actual moment acting on the beam, is less than maximum moment resisted by the beam. So that's why this beam is not fully loaded. So beam is under reinforced or under loaded, we can say under reinforced as well as under loaded, as whatever the capacity of the steel bars is there, up to that level this is not loaded. That's why it is under reinforced or under loaded, or still there is some strength. Okay, so once we have decided the bar, now we can use the formula to find out the quantity of the steel. So basically we have to find out simply steel required. So if you remember the formula, it is little bit big formula. AST equal to 0.5 FCK divided by FY, right? And then there is big bracket 1 minus, then square root 1 minus 4.6 mu, right? This is mu, actual moment, divided by FCK BD square, CK B into T square, right? And out of, again outside the bracket there is BD. So if you plug in all these values, just plug in 0.5 into 20 divided by 500 into 1 minus into big square root 1 minus 4.6 into mu is 60, right? But make it into Newton millimeter, because this is in kilonewton meter. So if we multiply by 10 to power 6, it will become Newton millimeter, right? And then because all other values are in Newton millimeter, so FCK is 20, B is 230, and D is 360, right? But square of that, so don't forget that. And outside the bracket there is BD. I will write it down here little bit below as I don't have the space. 230 is the B and D is 360, right? 360. So if you solve this, you will get the AST or area of steel required for this singly reinforced beam to resist the given moment, that is 60 kilonewton meter, will be equal to, so this is the final answer. AST required will be 442.4 millimeter square. That's it. Thank you.